Hi everyone, this video goes over starting on page 10 of the Unit 2 packet. The top of this page says limits of transcendental functions. So you may have never heard that word before, but transcendental functions are those that transcend or go beyond normal algebraic functions. So they include but are not limited to exponential functions, which is what we're going to look at in this video, and trig functions. So we're going to investigate the exponential functions now. So here are just a little review of exponential functions. You've got exponential growth, which if you graphed exponential growth, it would look something like this. And exponential decay looks something like that. So on the bottom it says categorize these functions below as exponential growth or decay. So for exponential growth equations in the what do you notice, this is going to be in general a base that is greater than 1. And then for exponential decay, the base is going to be between 0 and 1. Now, a couple of these aren't exactly perfect, so we'll talk about that. So 2 to the x has a base that's greater than 1, so this is going to be exponential growth. 3 to the x minus 2 plus 6, this is also going to be exponential growth. There is a 3 to the x right here, that's what's making it growth. The minus 2 and the plus 6 are just shifting the graph around. Now here I have 1/2 to the x, so 1/2 is our base, since that's the number with the exponent. The base is in between 0 and 1, 1/2, so this is going to be exponential decay. And then I'm going to skip over to j of x, which is 1/3 to the x plus 3. So this is basically like 1/3 to the x and then shifted. That's what the plus 3 is doing. It's actually shifting it to the left. But 1/3 to the x is going to be exponential decay. So the rest of them have something in common, which are negative exponents. So let's look at h of x. So h of x is 0.75 raised to the negative x, and then, plus 1. So the base here is 0.75. 0.75 in theory should be exponential decay, but when we graph it, we see it as exponential growth. The reason why we see it as exponential growth is because negative exponents, like if I typed in, so 0.75, instead of to the negative x, if I did that to the negative 1, kind of like negative 1x, I would get 1.3 repeating, which is 4/3. 4/3 or 1.3 repeating is a number that's greater than 1. So our base is actually a number that's greater than 1, so this is exponential growth. Now, like if I look at 5 to the negative x, I mean. So 5 to the negative x, if I graph that, 5 is our base, technically, and it should be growth, but it's decay. And again, the same thing is happening here. This is really 5 raised to the negative 1. I mean, if I'm really trying to write what I'm talking about, I would be writing like 5 to the negative 1 power and then to the x power. So the 5 to the negative 1 is going to make this 0.2 or 1/5. So this is really 1/5 to the x, which is actually decay. So anytime you see a negative exponent, it's actually like switching what's going on. So the 5, actually the negative exponent made it 1/5, which actually made it decay. So this one, this 2/5 to a negative exponent, 2/5 would really usually be decay, but because it's getting hit with a negative exponent, it's going to do the reciprocal, and it's going to make it growth. E to the negative x, so if you don't remember E is 2.718, so E would be a growth equation, but again, it's getting hit with a negative exponent. So it's going to be decay. So the base is greater than 1 for growth equations, or a base that's between 1 and 0, or 0 and 1. With a negative exponent. Same thing over here. Usually the base is between 0 and 1, or a base that's greater than 1 with a negative exponent. All right, on the bottom it says exponential functions have asymptotes. Where are the asymptotes on each of the following functions? So the asymptotes are where the graph approaches, and this is where we're kind of getting into the talk of limits. So if you graph 2 to the x, the asymptote is here. It's where the graph is approaching, so that would be 0. If you go to the table, you can kind of see that if you start going backwards, you're getting closer and closer to 0. 0.002, this is like the e to the -4 means you move the decimal point to the left 4 spaces. It's like scientific notation, so it would be like 0.000976, 0.0004, and so on and so forth. But you can see that it's getting closer and closer to 0. Now if you start changing this up, so the next one is 1/2 to the x, and then -3. Here's our decay graph, and look at where the asymptote is. If you had to guess, you might guess where the asymptote was, or you go into the table, and you can start seeing, okay, my graph is flattening out. Let me change this. All right, let me get some decimal values. Okay, and your calculator is just, it's not actually getting to -3, but it's getting so close that your calculator is just really estimating -3. All right, so the number on the end, that is where the asymptote is going to be. This one had no number on the end, so that's where our 0 is. This means the asymptote is going to be at +6, +17, +1. This has nothing, so 0. This one has nothing on the end, so 0. And 0 again. So the asymptotes are equal to the value of the constant that's being added or subtracted at the end. All right, so again, this is where limits are coming into play. So the limits are going to have to do with the asymptotes that are there. So if you go to page 11, we're going to look at the function 3/2 raised to the x minus 1 minus 3. So our asymptote here is going to be at -3. This graph is increasing. I'm just going to circle increasing. This is exponential growth. So as x approaches -infinity, that would be on the left side of the graph. The graph is approaching the asymptote, so the limit is equal to -3. On the right side of the graph, as x approaches infinity, the graph is pointing up, so the limit is going to be infinity as well. For the second one, we have a decreasing graph where the asymptote is also at -3. So that's this number right here. And so our graph is on the left side, as x approaches negative infinity, it's pointing up towards infinity. And on the right side, it's pointing towards the asymptote, which is -3. Now you're going to try to be able to do these without like looking at the graph. So 2 to the negative x, so you might be like, okay, 2 to the negative x, 2 should be growth, but since it's negative, it's going to be decay, so this is going to be decreasing. The asymptote is at -2. And so on the left side of the graph, since it's going to be decreasing, it's going to be pointing up towards infinity. And on the right side of the graph, it's going to be pointing towards the asymptote, which is -2. The last one on this page, 2/3, which should be growth, is not growth because of the negative exponent. So, or I'm sorry, which should be decay, won't be decay due to the negative exponent. So this is 2/3. You would look at it and think, okay, this should be decay due to the base being less than 1, but because of the negative exponent, it's going to be growth. So this is going to be increasing with an asymptote at 1. So as x approaches negative infinity, that's the left side of the graph. The graph is pointing towards 1, which is the asymptote. On the right side of the graph, it's pointing towards infinity. Now, what happens when you have something that looks like this? So these graphs have been reflected. And let's look at the equation. So what's different about these equations? What do they have? So it's this negative in the front. So e to the x minus 1 plus 2 has an exponent, or has an asymptote at 2. And this one also has an asymptote at 2. But instead of being a growth graph, which is what you would think, the negative makes it be reflected. This would have been a decay graph, like this, but the negative means it's reflected. So the graphs have been reflected over the asymptote due to the negative leading coefficient. So now the limit as x approaches negative infinity of f of x is actually going towards the asymptote, which is 2. And on the right, instead of pointing up towards infinity, it's going to point down towards negative infinity. On this side, on the left side of the graph, it would have pointed up towards infinity, but the left side is now pointing down towards negative infinity because it's been reflected. And on the right side of the graph is still approaching the asymptote of 2. All right, so the limits at infinity of exponential functions really can only tend towards 3 places. Option 1 is your answer might be infinity. So if you have an exponential growth graph and you're looking, let me write this. So say you're trying to do the limit as x approaches infinity of some function that happens to be exponential growth. That answer is always going to be infinity. Or if you have an exponential decay graph and you're doing the limit as x approaches negative infinity of some function f of x, that's a decay graph. That's happening again here and here. The second case would be if you got like a negative infinity answer. And that answer is only going to happen if you have a reflected graph. Otherwise, your graphs are going to look like this. So if you happen to have a reflected graph, it's possible that your answer could be negative infinity. So this is technically a reflected growth graph. and this is a reflected decay graph. I know I wrote reflected on both twice, but whatever. So the limit, if you had a reflected growth graph, it would be going up towards infinity here, but now it's going down towards negative infinity. So as x approaches infinity, this function that's a reflected growth graph could be towards negative infinity. It's the reverse of this, it's the reflection. Same thing here, it's the reflection of this, where it once would have been pointing towards infinity, it's now pointing down towards negative infinity. The only other option is the answer will be the asymptote. And so depending on, I know these asymptotes aren't in the same location, but if you have an exponential decay graph or some sort of reflected decay, then on the right side of the graph, which is as x approaches infinity, the function is going to tend towards, I'm going to write A for asymptote because I know these asymptotes are in different locations. And if you have a growth graph or some sort of reflected growth graph, then you're going to hit the asymptote on the left side of the graph. So I'll just write that in the same way. I'll write an A for asymptote. So we're going to try to do these without like looking at the graph. We can like jot down the graph what it looks like, but okay. All right, so I'm going to skip some of these and do some of the other ones. All right, so right now we're going to look at 2, 3, and 6. So this graph is 2 raised to the x minus 3. That is a growth graph. And with an asymptote at, I'm just going to put an A for asymptote at 4. So we can sketch it out. 1, 2, 3, 4, without drawing it on our calculator is what I'm trying to say. So it looks like this. It's growth, so it's going to look like that. All right, so as x approaches infinity, which is over here, the graph is pointing up towards infinity. This one is a decay graph, but then it gets hit by a negative in the exponent, so that's going to make this a growth graph. But then it's going to be reflected. And the asymptote is going to be at 5. 1, 2, 3, 4, 5. So this is growth. It would look like this, but you're going to flip it. Here, let me draw what it would look like. So without the negative in the front, it would just look like this. But with the negative in the front, it's going to look like that. So this one, the one in pink, is the real graph. All right, so as x approaches negative infinity, that's the left side of the graph is approaching the asymptote, which is 5. And then for number 6, I have 1/3 to the 2 minus x. So again, I have this negative in the exponent. I know that's in the reverse order, but it's still a negative x. So this should be decay, but it's actually going to be growth. And it's going to be reflected. So 1, 2, 3, -3 for our asymptote. And again, normally, I'm going to draw the normal one in blue. So normally this would look like this if it was a growth graph, but we're reflecting it, so it's going to look upside down. So as x approaches infinity, which is on the right side, the graph is pointing down towards negative infinity. All right, let's look at 7 and 8 as well. So 7 and 8 give you the graph. It says, using the graph of f of x at the right, find each of the following limits. So the limit as x approaches infinity, so that's the right side of the graph, is pointing towards the asymptote, which is -3. And the left side of the graph is pointing up towards infinity. Now, the ones that I skipped over are the whole number values. So let's look at number 9. So number 9, as x approaches 0. So 0, this is a continuous graph. So 0 is at 1. So the limit from the left is 1 and the limit from the right is 1. So the limit is equal to the function's value because these exponential graphs are continuous everywhere except, well, they're continuous everywhere. At 2, the limit is -2. The limit from the left is -2. The limit from the right is -2. So it's -2. Now, how could you get these values without a graph? So if you're asked something like this, if it's just a number value, so -2, you can just substitute because these are continuous functions. So the only ones you have to be cautious of, like what's happening, are the ones that where they approach infinity or negative infinity. But if they give you any other number, you can just substitute. So 3 raised to the -2 plus 4 minus 2. -2 plus 4 is 2. 3 squared is 9. 9 minus 2 is 7. So that just really means the point -2, 7 is on your graph. On this one, we're approaching 3. So again, it's continuous. So I'm just going to plug in 1/2, and then 3 minus 3 minus 1. 3 minus 3 is 0. Anything raised to the 0 power is 1. So this is really 1 minus 1, which is 0. So that just means that the point 3, 0 is on the graph. And then for this one, as x approaches -1, again, you're just going to substitute -4, and then -1 minus 1 plus 5. Negative is a positive, so just 1 minus 1. So this is really -4 to the 0 plus 5. Anything raised to the 0 power is 1, so this is 4. 4 to the 0 is 1, but with a negative out front, it's going to be -1. And then plus 5 is 4. All right. So on page 14, this chart says, complete the chart without looking at their graphs. So try to do this without looking at the graph, just by getting a general sense on what's going on. So 3 halves to the x minus 1 is a growth graph. I'm just going to go like this on the side, so I know what it looks like. And I know that the asymptote is at -3. I'm just going to put -3 next to this. I just put a box around it because I thought it kind of looked like a part of the dotted line, the negative. All right, so I have this kind of graph. I know that it says without looking at their graphs, I mean like without actually graphing it. So the base is going to be considered to be 3 halves. This one is increasing. The limit as x approaches -infinity is going to be the asymptote, so -3, and then the other side is approaching infinity. This one is negative e to the x minus 1. So there's no negative in the exponent in front of the x, so it's just going to be a regular old growth graph. Increasing like this. And the asymptote is going to be at 2. I'll put a box around it for consistency. All right, so our base here is going to be e. Oh wait, I messed that up. Because what's happening? This is a reflected graph. So for a reflected graph, this is really the true graph. All right, so we have that. This graph is technically decreasing since it's going from here to there. And on the left side of the graph is approaching 2, which is the asymptote. And on the right side of the graph, it's approaching negative infinity. The last one in this section is 2/3. So our base is 2/3, but it's getting hit by a negative exponent. So our base is technically 3/2 since it's getting raised to the negative first power. So I'm just going to put 2/3 to the negative first. So that's really 3/2. So this graph, so my asymptote would be at 1. And this, wow. And this graph that looks like it's decay would actually be growth. So this graph is increasing, and on the left side of the graph, it's approaching 1, and on the right side, it's going up towards infinity. For the decay section, all right, for the decay section, I have 1/2 to the x minus 2 and then minus 3. So negative 3 is where my asymptote is going to be. And my graph is decreasing towards the asymptote. So my base is 1/2, and my graph is decreasing. On the left side of the graph, the limit as x approaches negative infinity is positive infinity, and on the right side of the graph, it's approaching the asymptote, which happens to be at negative 3. For the next one, I have 1/2, again, to the x plus 3. So I've got a positive exponent here, so it's just going to be an exponential decay graph. And the asymptote is at 2. I'm going to do what I did up here. I know this was a mistake, but I'm going to do it anyway down here. So 1/2 would really mean I'm going to do a decay graph, right? But that's actually not the graph that we're looking at because the graph is a reflection. So I'm going to reflect this graph over the asymptote so it really looks like that instead. All right, so my base here is still 1/2, but this graph is actually increasing technically. On the left side of the graph, it's pointing down towards negative infinity. So the limit as x approaches negative infinity is negative infinity. And the right side of the graph is pointing towards the asymptote, which happens to be at 2. And then the last one is 2 to the negative x. 2 would really be a growth graph, but the negative is making it a decay graph. The asymptote is at negative 2. And we're going to do decay. Technically, the base is 2, but it has this negative, so I'm going to say that the base is 2 to the negative first, which is really 1/2, which makes it look more like a decay graph. So my graph is decreasing. And my limit on the left side of the graph is pointing up towards infinity, and the limit to the right On the right side, as x approaches infinity, is the asymptote, which is -2. All right, go ahead and try practice number 3.